All right, so welcome back to the Civil FE exam review. Today in this video, we want to continue our Geotechnical Engineering section of the review, and we're going to be focusing specifically on a laboratory and field test. So I have a few problems that I want to go ahead and dive right into. All right, so number one says, zoom in a little bit. So given information, you have a constant head permeability test results, and those test results are your hydraulic conductivity is equal to 1 times 10 to the negative 5 centimeters per second. You have a cross-sectional area that equals 20 centimeters squared, and you have a change in hydraulic head that equals 1. Determine the flow rate, Q. Okay, so this is a bunch of information that they're giving me, and so what I want to do is write out the given information and then the information that I'm trying to find and any formulas that I may need to use. The information that I'm giving the hydraulic conductivity. We're also given the area, and we're given the change in head. Hydraulic head specifically. We're trying to find the flow rate, or Q. All right, so any formula is needed. Okay, so if I'm trying to find the flow rate, or if I'm trying to find Q, just from my knowledge of some of the practice that I did in fluid mechanics, I know that if I search flow, I get 278 results. So I'm going to try to use something that they gave me to see if I can narrow down my formulas that I can choose from. So I'm going to search hydraulic conductivity. Okay, and only 5 results come up for hydraulic conductivity. So I'm going to see if that's a variable that I can use to plug. All right, so hydraulic conductivity here is going to be K, which equals Q. Q is the total quantity of water. Don't know what units those are. I is going to be change in head over change in length. We are not given the length of the soil column. A is the cross-sectional area, test specimen perpendicular to flow. Not necessarily, and this is a reservoir too. And this is that there's a period of time that you need. So don't think that's the right formula. For this one, Darcy's law, we have a negative K, which is the hydraulic conductivity, which we do have. Okay. What about A? The cross-sectional area of flow. We have that. And then, so Q is equal to negative K. So Q is my flow that I'm searching for. Discharge rate, flow rate, same thing. And then dH over dx. What's H? Hydraulic head. So it's the change in hydraulic head, right? And so that would be 1 in this case. So I have all the things that I need in order to get my answer. All right, so let's write the equation out and then solve. All right, so the formulas needed is Q is equal to negative K A and then dH over dx. I'm going to write out each variable. Q is equal to question mark. That's what we're solving for. K is equal to my hydraulic conductivity, which is 1 times 10 to the negative 5 centimeters over seconds. Key to note, all of my answer is in centimeters cubed over seconds. So if things are in centimeters or if things are in seconds, then that's perfect. Okay. All right. A is equal to cross-sectional area, which is equal to 20 centimeters squared. And then dH over dx is equal to hydraulic head, or change in hydraulic head, which is equal to 1. All right. So plug and chug. Q is equal to 1, or sorry, a negative K. It's negative 1 times 10 to the negative 5 centimeters per second times my area, 20 centimeters squared, times my change in hydraulic head, which is equal to 1. When I multiply all this out, I get negative 2 times 10 to the negative 4 centimeters cubed divided by S. Or same thing as A. Answer is A. All right, let's look at number 2. So it says, during a construction project, a soil sample underwent a Proctor test, resulting in a dry density of 1,950 kilograms per meter cubed at an optimum moisture content of 14%. What does this information suggest about the soil's compaction characteristics? Okay, so let's write out what we're given. We are given the dry density, and we're also given the optimum moisture content, right? And we want to find what this information suggests, right? Okay, so when you have dry, so formulas needed. Are there any formulas that we would need for this? Based on the answer choices, okay, let's just go through them. The soil is overcompacted, leading to reduced stability. The achieved dry density is below the required specifications. We don't know the specifications. So to me, that's a bad answer. The moisture content is within the optimal range for compaction. Okay. And the dry density is not relevant parameter for soil compaction. All right. So it looks like we're going to need some prior knowledge here. So some things that I wanted to bring to your attention is that when you get a optimum moisture content of 14%, typical optimum moisture content is between 10 and 20%. Okay. And so being that they got 14%, that's a good sign, right? And also lets you know it corresponds to how compact your soil will be. So if you have too much moisture, right, it's going to reduce your stability, right? It's going to be too wet. Your soil is going to be too wet if you have too much moisture. And so if you just think about that, if you have soil. Just draw like, if you have this weird puddle, right, and it's soil, but it's so much water has gotten into it, you know, that it rained on it and got in it, and the soap has soaked in it. It's going to be a puddle. So you can't put you wouldn't want to put a gigantic home in like a swampy area, right? You just think about that. Why would you put a home there, right? Because it's not going to be stable. Anytime you have an unstable home, you know what happens, goes down, right? So I'm just thinking about that when you want your soil to be as compact as possible. So the more optimum that range is, the better. So so if we look at this for answer A, the soil is over compacted, leading to reduced stability. If it's over compacted, that means it's not moving. That means you got as much dirt in a certain amount of volume as possible. And typically, I would go out in the field and would test soil compaction sometimes, and they want it to be pretty much at 100%, if not, it needs to be at least 95% compact, right? Up to 100 percent compact. So over compacted, if it's 101%, which sometimes those things read pretty high. So if it's 101, that means it's this is really stable, so it doesn't reduce stability. So A is no. The moisture content is within the optimal range for compaction. Yes. Right. And then dry density is not relevant parameter for compaction. That is false. It is. Alrighty. So we get C for number 2. Let's look at number 3. In a geotechnical investigation, a consolidated undrained triaxial test is performed to determine the undrained shear strength of a clay soil. How does the undrained shear strength influence construction activities, particularly in slope projects? Right. Okay. So the information that given is that you're doing a triaxial test, checking for undrained shear strength. Okay. Okay. And so you want to find how undrained shear strength will influence slope projects. All right. So what formulas might you need for this? So based on my answers, higher undrained shear strength and simplifies construction activities, so less attention to soil stability. So we need to see what happens with slope projects first. So what's a slope project? Well, it's where you're trying to get you have basically you have ground where it's sloping up or down, right? This is gonna affect where water goes, and you know how how your where the soil goes to, because if you don't have enough if you don't have enough um, you know, soil that is able to hold itself up, right? You could get slipping where the soil collapses, kind of like if you think about a rock or a mountain, right? Sometimes over time, your mountain may turn into a smaller mountain where this top piece slides off, right, to slipping, and it's that slope is similar, and it happens with soils as well. Okay, so enough with these pictures. Now, if you don't have prior knowledge on this, it's a good thing to kind of note something called slope failure. Slope failure. And the handbook gives you an image of what slope failure can look like. And so things you want to pay attention to is the forces that are acting, along the dirt, right? So you got your assumed planar slip surface, and you have T mob, and it's pointing down. All right, what is T mob? It's the mobilized shear force along the slip surface. So that's the force that's pushing downwards for this thing to slide. And then you have TFF is pushing upwards, where it's the available shearing resistance along the slope. So you got force coming down, and then you have force that's trying to counteract this thing and make sure that this does not slide along the slip surface. So when we look at this, right, this deals with shearing resistance, and shear force. So let's look at A. The higher undrained shear strength simplifies. So higher shear strength or shear force over a particular area simplifies construction activities requiring less attention to soil stability. And I would disagree. If you have more shear strength, which means you have more force coming down, then you definitely need to pay more attention to slope stability, because this thing it may not have the amount of resistance that it needs to be able to hold up all that increased or higher shear strength. So I'd say 3 is wrong. I mean, A is wrong. Not 3 is wrong. So A is wrong. Lower undrained shear strength necessitates additional stabilization measures during construction. So if we lower the amount of amount of force coming down, is that gonna provide additional stability to our construction? And it will. It will. So that one's correct. I mean, if you think about it too, right? It's going to be easier for the force to come down because of gravity and things like that versus the resistance going up, right? So the lower we can decrease the force coming down of the soil, the better and the more stable our project and our soil is going to be, our surface is going to be. All right. So undrained shear strength has no impact. So shear strength does have an impact on construction activities. So I would say that's wrong. And the construction process remains unaffected by undrained shear strength variation. So if it varies in shear strength, The construction process remains unaffected. No. So best answer would be B. So this is conceptual. Something to think about. Just remember that your slopes can have resistance or it can have force along the slip. So this concludes the laboratory and field test portion. In the next video, we'll be looking at effective stress.